Let's begin the second lesson in this chapter with a little bit of review. First, the empirical rule. The empirical rule was a very useful application of bell-shaped distributions, which we now know as normal distributions, where we could determine the amount or the percentage of observations between standard deviation markers in that bell-shaped curve. For example, we knew that 68% of all observations fell within one standard deviation of the mean. We also knew that 95% of all observations under the curve fell within two standard deviations of the mean, and finally 99.7% of observations fall between three standard deviations of the mean. You'll notice that this specific curve I have drawn here is broken down even more. You might even notice that some of the values in here are possibly answers that you've seen along the way on some of your empirical rule practice problems. For example, these 34s right here are just 68 divided by 2 by symmetry. These 13.5s are 95 minus 68 divided by 2, something that we did, I believe, in class. And our 2.35s, which are here, are 99.7 minus 95 divided by 2. Finally, 0.15% here are going to be 1, which is the entire curve, minus 99.7 divided by 2. Is this something you have to memorize at the bottom of these percentages? Absolutely not. These are just a clever way of showing some of where the areas actually fall in this, and also helps students see the symmetry going on with the normal curve. Another topic we covered for bell-shaped curves was z-scores. Now, z-scores, if you recall, were the number of standard deviations away from the mean. And we specifically used a nice formula that was z equals x minus mu over sigma. So whatever value we're trying to convert, we have our population mean, so I'll say pop mean, and we have our population standard deviation. Also recall that z-scores are measures of position. They can help us place where observations are located in their respective data sets. For example, we were comparing a student who took the SATs to a student that took the ACTs, and we were trying to determine which one of them scored higher on their respective test. Z-scores, of course, allowed us to accomplish this task, but it turns out that they have a much bigger role to play in the world of statistics. Specifically, if you gather up all the z-scores together, they actually form their own special type of normal distribution. So what exactly does that distribution look like? Well, let's figure it out. Remember that z-scores represent the number of standard deviations away from the mean. So take a peek at this guy right here. This is telling you that you are going one standard deviation above the mean. So that implies that that would be a z of plus 1. This is going 2 standard deviations above the mean. So that would be a z of plus 2 and plus 3. On the other side, this value here represents 1 standard deviation below the mean. So that would be a negative 1. This is 2 below the mean. This is 3 below the mean. The only one we don't have is what would mu represent. Well, mu, I think most of you can see that it's halfway between negative 1 and 1, so it's clearly going to be 0. But we can prove that by just taking, remember this value here is what we're converting. So if we wanted to convert mu, we could just plug it right in here and get mu minus mu, which is 0. And 0 divided by sigma would give us 0 anyway. Therefore, our new distribution of z-scores is going to look something like this. 0 in the middle, We have -1 and 1 at our inflection points approximately. Remember those. And then space out the integers going by 1. All right, so this is called a standard normal distribution. So to be clear, there is only one standard normal distribution, whereas there are infinitely many just ordinary normal distributions. The standard normal distribution will have all the same traits as a typical normal distribution. It happens to be above the x-axis. The area underneath it is going to be 1. We've already said what the mean and standard deviation is going to be, because here's your mean, mu, and here is your standard deviation, sigma, which is clearly 1. So we would say, with our label that we know very fondly, we would say it is normally distributed with a mean of 0 and a standard deviation of 1. So why are standard normal distributions so important to a statistician? We remember from our previous lesson, we talked about finding area under a curve for uniform and bell-shaped normal distributions. For uniform distributions, it was quite straightforward to find the areas because we knew the area of a rectangle. So computing those areas was pretty simple. When we moved to our bell-shaped normal distribution, we were asked to find the area below 200, and that would require finding this area. Now that area, in terms of the shape, is not something we know geometrically, which means finding it is basically impossible. As a matter of fact, the problem itself had to explicitly give us that area because there was no way to find it. So what the standard normal distribution does is it gives us a way to actually find areas underneath that curve. How does it do that? It actually has an entire table of areas associated with it. This is called the standard normal table. Often, for short, it's called just the z-table. Makes sense because the standard normal distribution is a distribution of z-values or z-scores. So what does this standard normal table do? It effectively allows us to find the area below any z-value that is provided in a standard normal distribution. For example, let's say that we wanted to know, we'll just number these, the probability that a value of z is less than 1.15. First thing to do is we have a picture of the standard normal distribution that we can visualize this entire process. So we want to find 1.15 on the graph, which will be approximately right there. So what I'm going to do is I'm just going to draw a line above it, 0.15. This is asking for the probability that any z-value falls below 1.5 on this graph. And if that's the case, remember that probability and area have a synergy where they're 1-to-1. So that's the probability of this occurring, is asking for the area under the curve below 1.15. So what we can do is we can basically just shade in this region. So we'll work our way to the table in 1 second, but just realize that we cannot use the empirical rule here. Remember, the empirical rule is specifically only for standard deviation markers that are at the integer values. So we can use all of these numbers as long as the z-value is 1, 2, 3, -3, whatever it is. But right now, this 1.15 would fall like right here. We don't know any of the areas associated with anything in between the standard deviation markers, hence why the standard normal distribution is so important. The next order of business is now to learn how to use the z-table. This is going to be an incredibly important skill going forward, which means you must learn it. And in your next course, if you have to take Stat 2, it will be important there as well. First thing, there are two sides to this table. One side deals with the negative z-scores. That happens to be this side. And you'll see along these row values that are here, there are all negative symbols in front of the numbers. Whereas the other side deals with positive z-scores. You can see again, the negative values are no longer there, which implies that these are going to be positive. If you recall, going back to the problem at hand, we were looking for the probability that z was less than 1.15, which means the z-score of importance that we must deal with is 1.15. So going back to the table, we clearly are on the wrong page because this is a negative. These are negative values. So we need to go over to our positive version of the z-scores and realize we're trying to find 1.15. So if you look closely, you'll see the variable z is located right here. It turns out that all of the numbers in these rows are going to be essentially the 1 spot of the number and the 10th spot of the value, whereas these numbers are going to be the 100th spot. So think of it this way. Think of it as breaking up the number into two pieces. So if we were to break up the z-score, this would be 1.1 and this would be 0.05. If we added these together, we would get 1.15. It's kind of a weird way to split up the numbers, but it's very effective when it comes to finding the appropriate area. So again, this part here is going to be what's going on here. And then this part with 0.0 in front of it is what's going to be going on the top. So let's find this number specifically. So we need to find 1.1, which is right here, and we need to find 0.05, which is right here. The next step is to just simply meet in the middle. Follow the 1.1 row all the way through. Follow the 0.05 column all the way down until you meet at a specific area value. This value is 0.8749. What does this mean? Every single area that is in the body of either side of this table will always be the area below the z value that you look up, which means in our problem here, where we have shaded the area below our value of z, 1.15, we have now determined that this area is 0.8749. Let's try one more of these before we talk a little bit deeper about what this means for us. So again, let's try to find the probability that a z value falls below negative 0.24. Again, remember, the most ideal thing to do would be to get our curve drawn. We're going to find negative 0.24 wherever it falls. That's probably going to be about right here, right? We're going to draw a line above it. And we're going to shade in all the region below. We are therefore looking for the area that is shaded. That is our goal. So we go to the z table, and this time we have a negative value of z. So it is negative 0.24. Well, how would that split up? That would split up into negative 0.2 for the first two pieces, and then 0.04 for the last piece. So we would go into our z table, we would find negative 0.2, which now unfortunately is a little bit farther down. It's all the way down here, but we still have some vision here. So remember, we're going also to 0.04, which is here. We're going to then meet in the middle, all the way down, and we're going to find the numbers 0.4052. That means that the area we just found is indeed 0.4052. It is important that students remember a few things that help them with these computations and this process. One is, remember, no matter what the normal distribution you're dealing with, you can split the area perfectly in half because of the symmetry of the distribution. So we know that the area underneath a normal curve is 1, which means if we go this way, we're going to have an area of 0.500. And if we go this way, we're going to have an area of 0.5000. Why is that helpful? Well, when you get your z-score and you shade in your area, for example, we started with this guy here, right, 1.15, the area you shade in here clearly is more than half of this curve, which means the answer should be more than 0.50000 worth of area. Same thing goes for our other z-score, which is clearly on less than half the curve when you shade in below it, this guy here. That means your answer should be less than 0.5000 and so forth. You have no idea how many times on an exam a student gets something very similar to this and then looks up the value of z in the table incorrectly and gives me an area that is less than 0.5. It just doesn't make any sense. The more you understand how the area works under the curve, the less likely you're going to make a mistake. Before we move to some more examples, I just wanted to dig a little deeper here and give students some context to exactly what we're doing right now. So just remember, there are infinitely many normal distributions. For example, the popular one we've been using is SAT scores. If we tried to analyze the distribution of SAT scores, it would be very challenging to do directly because there is no table of areas for that distribution. Just like there is no table of areas for any of the infinitely many real-world normal distributions. So what you want to think about is the purpose of a standard normal distribution and learning about it is to use it as a tool to get to the z-table and the areas associated with the z-scores in that z-table. Okay, so let's do a few more examples of areas below just to help student understanding of how the curve works. So let's say that in number 3 here, that we're trying to find the probability that z is less than negative 4.25. Let's move on over to the z-table and see what's going on there. Remember, we're dealing with negative 4.25. So we need to be on the negative side of the table. Looks like we're already there, which means we need to find negative 4.2 on this side. If you look at all the numbers on this side, we start at negative 0.0 and we go to negative 3.4. Unfortunately, negative 4.2, which is what we're trying to find, is not there. So what exactly does that mean for us in terms of finding this area? Well, the first thing you want to do is just realize what the lowest z value is on this chart. And the best way to do that is literally just take your 3.4 and then go all the way to your 0.09 over here. And then find the area that it's associated with. So our lowest value is z equals negative 3.49, and it's associated with an area of 0.0002 below. If we go back to our problem that we're dealing with and we try to map this out, you're going to see that we are way off the beaten path here. So negative 3 is here, which means negative 3.49 is going to go way out here. So let me just, first of all, try to find negative 4, try to be even here. And then what I'm going to do is I'm going to mark negative 3.49. And if I was the shade, which really there's not really anything to shade here, which should imply something to you, then that area to the left of this is going to be 0.0002. Okay, that's the first thing. Therefore, if in this problem, which is the actual thing we're trying to find, if I'm trying to go to negative 4.25, then the area below that is going to be even less. And the key here is if we're going less than this, we're basically heading towards 0.0000 in terms of area. Now, that still means that there's area out there, because the area out there could be, 0.00000072 or something like that. But in our course, we're going to concentrate only on 4 decimal places. So if we have a decimal to 4 decimal places that's all zeros, then we're always just going to say approximately 0, which means this probability is approximately 0. The honest truth here is that is sometimes tricky for students to understand. The key is that, remember, we have a curve. The area underneath it is 1, right? We know that's the case. And you can clearly see that this curve, as it heads towards down here, there's smaller and smaller area underneath it. So when you get outside the value of the lowest value on the chart, which is negative 3.49, you're just going to assume that there's approximately 0 area outside of that from now on. That's the best thing to do. Okay, so what about this guy? Probability that z is less than 3.95. All right, so again, we're out here somewhere. So that's right there is about 3.95. We're looking for the area below that. Okay, so the same logic should hold here, in the fact that there's very little area out here, right? Underneath this curve right here, there's just no area. So therefore, if there's very little area over there, in other words, approximately 0, then how much area has to be below it? Well, what's below it? Basically the entire curve. So therefore, we would say that this area is going to be approximately 1. So clearly you'll notice that I did that logically. I didn't even go to the table, but the table should back me up. So if I go to here to the positive side, which is 3.95, is what the z we're looking for, right? Well, again, what am I going to do is I'm going to try to find 3.9 on here. Well, 3.9, again, doesn't exist. It's down here somewhere, right? So what is the highest value? It's 3.49 positive, just like negative 3.49 was the lowest. So if I follow that to here, you're going to see that this is really close to 1. It's 0.9998. So if the area below 3.49 is 0.998, then the area below 3.95 is going to be approximately 1. And you can assume that any value off this chart in the positive direction, higher, once again, that z-score will produce an area of approximately 1. Okay, moving on. It's important to realize that you are not always going to be asked for probabilities associated with z's that are less than. So that's what we have to conquer next. We'll do this all by example. So probability, let's say that z is greater than 1.06. First thing to do is to locate 1.06 on the curve, which should be about right there, I would say. And then we want to put a nice little line above it in the graph. Remember, we're looking for greater than, so this time we're shading this way. Remember, the goal here is we're looking for this area, but if we look up this number in our table, the table only gives us areas below. So if we look it up in the table, we're going to get this area on this side, but we want this area on this side. How do we pull that off? Very easily. We know that the area underneath the curve, totally, the whole thing, is 1. So all we have to do is look up 1.06, find the area to the left of it right here, and then subtract from 1, and that's going to give us our missing area. So let's go ahead and do that. We go to the z table. We're going to find 1.06. which means we're looking up 1.0 and 0.06 on the positive side. That is going to give us 0.8554. So this is 0.8554. Now, let's say you made a mistake and you go, no, that's the answer, 0.8554. That does not make any sense. If you wrote 0.8554 here and pointed to this right here, this is an area that is clearly less than half the curve. It should be less than 0.50000. So be very careful with the way you do things with that. Wrong answers are usually very easily caught as long as you understand the curve. So again, what are we going to do for this? All we have to do is do 1 minus 0.8554, and that is going to give you 0.1446, which is the answer to the problem. Okay, let's do another. 6. Probability that z is greater than negative 2.37. Again, what do we want to do? We want to have a nice picture of this so that we can draw it out. Negative 2.37 looks like it'll be about right there. We're looking for the area above it, which is all of this area right here, negative 2.37. We're going to go to our table. We're going to go to the negative side, which I believe is the top one. There you go. All right, negative 2.37 is what we're looking for. So we're going to look over here, negative 2.3, 0.07. We're going to make our way over, and it looks like we're going to find 0.0089. Okay, the key, though, is that is going to be the area below negative 2.37, 0.0089. So therefore, in order to find the area above, I have to do 1 minus that, which is going to give you 0.9911. Now, again, if for some reason you had circled this as your answer, let's say, right? That would have not made sense because this shaded area that we put here is greater than half the curve, and this is very little area that we're dealing with there. So answer for this is 0.9911. So far we've dealt with areas below and areas above. There happens to be one more very common type of area type that you often see, and it's the area between. So for example, the probability that z falls between negative 1.5 and positive 1.25. Okay, so what does that look like on our graph? Well, we're going to locate negative 1.5 here, positive 1.25 approximately there. We're going to draw lines above them, and we're going to shade in the area between these two numbers. Our goal is to find this area. Now, there is a unique strategy attached to this, just like there was in the greater than problems or the above problems. What you're always going to do is you're going to first find the area below the bigger z-score. If you do that, that's going to give us basically this area. Now, that's too much, way too much. So how do you decipher what you need to do next? Well, if you look at the shade that I have here, we want the area where there's both red and blue shading. What we don't want is we need to take out the area that's just blue that is over here. Well, if you think about it logically, that area is the area below negative 1.5. So all we have to do basically is find that area and subtract it from the other one. So again, just to be clear, when you want to find the area between two z-scores, you're going to find the area below the bigger z-score and then the area below the smaller z-score, and all you have to do is subtract them. Let's do exactly that. We'll find 1.25 on our positive side first. 1.25 will be here, 1.2.05. We're going to do our usual meet in the middle situation, and we're going to get 0.8944. So this right here, 0.8944 will be the area below 1.25. So that would be all the blue shade in my graph there. Now, I need to take out all of this area so that I only have what's in the middle. I can find that by looking up negative 1.5. Now remember, if it says negative 1.5, that implies that there's a 0 there. So then we have to go to the negative side of our chart. We have to find negative 1.5 and then just a 0 and meet halfway, and we're going to end up with 0.0668. So that is going to be this, which means if I want to find this area right here, then I have to do 0.8944 minus 0.0668, and that is going to give me 0.8276. So in summary, you'll see that I have a sort of a write-up here on how to find a shaded area in a curve. Anytime you have the area to the left of z, then all you need to do is look at the z value up in the table, and it's going to give you the area that you want, because all the area in the table is to the left. If you're trying to find the shaded area to the right of z, then you're going to have to take 1 minus the area to the left over here, because there's 1 in the curve, as was explained. And lastly, if you're trying to find the area between two z values, you take the area to the left of the larger minus the area to the left of the smaller. Just remember, though, you never manipulate z-scores. Students run into trouble when they start like adding and subtracting or doing things with z-scores. Remember, they're ironclad. Those are the position in which the actual data value is located. The only thing you're ever subtracting or changing is the area.